Okay, just about ready to get going, everyone? Perfect. All right. Just give another moment for folks to find seats. While we're doing that, I'll just give a quick introduction. So this session is all about Couchbase Server's architecture. And so introduce myself. My name's David Haikney. I'm the Director of Engineering for Couchbase, based in Manchester in the UK. And this is Dave Rigby, my colleague also from Manchester. And Dave Rigby is the technical architect of the data service within Couchbase. So really nice to be back at Connect. I've already seen a few familiar faces and hopefully some new ones as well. It's also very exciting to be here on election day. Although, oh, sorry, don't go there. I'll start with a warning though. As a Brit, we've got a bit of a tricky relationship with sort of democracy and voting at the moment. It's complicated. Onto the serious business. So the talk here for the next 40 minutes or so is to give you an overview of Couchbase Server's architecture. There's an awful lot to cover. It's a product that does a hell of a lot, so it's going to be very fast. We're going to go quite quickly through it, and deliberately so. We're going to do in kind of two phases. Firstly, we're going to talk about some of the fundamentals of the architecture that underpin many of the services the product provides. And then once we've done that, we're going to concentrate on the services themselves and peel off one layer and talk about how they are constructed, how they interact with all of the other services, to give you a flavor of what's going on behind the scenes. We've got a very, very busy agenda here at Connect over the next couple of days. So what we're going to try and do, as Mike did in the previous session in this room, is give you some pointers along the way as to other sessions that are going to be of interest. Given that this is an architecture presentation, I'm going to warn you now, there's going to be a lot of rectangles with various different names and words in. We're going to try and mix it up a little bit and show you some demos of what it actually looks like in the product itself. Dave's going to go as deep as give you a thread dump of some of the activity within the data service, so something else to look forward to there. So let's get going, and we'll start with these concepts. So I've got three of them that I'd like to take you through. For those of you that have been following Couchbase for a while, some of this might be familiar to you, and for those of you new, this is important stuff. These are some of the things that underpin Couchbase. So you're going to see pictures like this probably quite a bit over the next couple of days. This is a very simple block diagram of a Couchbase server node where all of the different services are broken down. You see the cluster manager at the top. That's responsible for kind of chatting to all of the other nodes within the cluster, making sure they're healthy, presenting the UI and a bunch of stuff. So that runs on all of the nodes. But it's the other services that are of interest here. So we have a concept that we refer to as multidimensional scalability. And what that means is you basically get to pick and choose which services are important to you. And you can, when you create a Couchbase cluster, you can select on which nodes you want which services to run. And this gives us a couple of good advantages. One is you only pay for what you use, and you can tune your resources to your specific workload. So if you've got a big data set, you can emphasize the data nodes. If you've got a heavy query workload, you can ramp up and you can scale up those query services. So the ability to scale each of these services independently means that you get the best resource utilization out of your hardware. So obviously, Couchbase as a product doesn't always often operate independently. You'll have a cluster of nodes. So here in this representation, I've got 6 nodes. And with the basic blocks that you can see there, the colored rectangles are kind of representing that all of the services in this deployment are running on each of the nodes. Perfectly valid topology. We see this quite a lot in development and test environments where people don't want to be, there's no need to be too careful about which services are running where and when. A more realistic production deployment would be something like this. So this is a 6-node cluster. 3 of the nodes are running the data service. 2 of them are running the index service. And the final 6th node is running both the query and FullText service. And again, we're going to dip into shortly to explain a little bit more about each of these services, what they do and how they operate. And so the first concept to familiarize yourself with is exactly that, the ability to select different services and to scale those independently as your data set grows, as your indexing requirement grows, as your query requirement grows. So here's the first of the little check marks for other session. So having all of these services begs a few questions. One is, how do I get it right? How do I know how many of this type of node I need? How many resources do I need to give to the indexing service, the query service? So there's a talk coming up immediately after this in Great America 1, which I think might be next door, on how to correctly size and configure your cluster. What are the do's and don'ts for setting up a cluster topology? That's going to give you an appreciation of what some of the considerations are, how to do it right, how to do it wrong. The other question with all of these services are, when I'm writing an application, which one's right for me? Should I be using key value? Should I be using nickel? Should I be using full text? And so a session coming up tomorrow at 2 p.m. by Michael Nitchinger, our Java architect. He's going to talk you through planning an application and which is the right service for you, which is the right API to be using for your use case. The second concept, and again, this will be familiar to those of you that have been with Couchbase a while, is our automatic sharding of data. So the fact that the cluster and the SDK cooperate to automatically evenly distribute your data across the cluster. This is something as an application developer you don't need to worry about. And the way this is achieved is through all of the data within Couchbase, all of the documents get stored in a bucket. And we break that bucket down into 1,024 little pieces, virtual buckets, or V-buckets as we call them. We sprinkle these V-buckets evenly across the data nodes in your cluster. And that gives us a very smooth, this is where some of our performance comes on, it gives us a very smooth distribution of the data. And it means that all of the data service nodes are all pulling an equivalent amount of weight. They have roughly the same number of documents, they're doing roughly the same number of operations, you don't get any hotspots. And the way that this is done is as follows. So I have an example document here with the key connect 2016. And so when an application wants to access that key, we will perform a hash function on that key, a CRC32 hash, and that will result in a number basically that points to one of our 1,024 V-buckets. And we introduced this level of indirection here, the table where you say V-buckets to server. That's our cluster map. That tells the client SDK which server is responsible for the data on that V-bucket. So in my example, the key hashes to V-bucket 27, and the cluster map tells the client that V-bucket 27 lives on server B. And so that's how the application knows where to access that data. And because we have these V-buckets, these shards, automated shards of the data set, this allows us to, one, take a replica copy of all those shards and put those on different nodes so that if one of the nodes fails, there's another node in the cluster that has a copy of that data. That's where some of our availability comes from. We also have the ability to evenly redistribute when you add capacity, when you add another data node. We can shuffle around, we call it rebalance, and we can move some of those V-buckets onto the new node. Let's take a quick look at what that looks like. So here I introduce a new server, server D, and it just so happens that my V-bucket 27 has server D enters the cluster manager gives it some of the V-buckets from the previous 3 nodes, and the cluster manager then pushes a new version of the cluster map up to our SDK. So again, this is all seamless, it's all online, it's all transparent to the application. The application is not aware that the data is moved, but the SDK has a new version of the cluster map. That key, the hashing is predictable, so that key will still hash to exactly the same V-bucket. It'll still land in V-bucket 27, but now the cluster map says that V-bucket now lives on node D. And so you've dynamically expanded your cluster. The application has been completely transparent to the application. So this V-buckets are a very important concept when you look at Couchbase's architecture. And then the third concept, before we move on to the services, is some of the plumbing that goes on behind the scenes. How does the data, once it's been received from the client, how does that propagate around the cluster to all of the other services? How do we make the replicas? And the answer to this is our replication protocol. We refer to it as DCP, the Database Change Protocol. So this was introduced in Couchbase Server 3.0, and it's crucial for many of the functions that Couchbase Server performs. So it's a high-performance protocol, so when a mutation is received or an update is received from the client in memory, it's then sent immediately across the network, for example, for replication, so that another node has a copy of that data as quickly as possible. Every mutation, every update that we send via DCP, via this replication protocol, is given a unique sequence number for that V-bucket. And what this means that every client that's connected, everyone that's listening to this stream of events, this stream of updates coming in via DCP, gets exactly the same sequence. So it's very consistent, very predictable. It also means that if one of these clients temporarily disconnects and then resumes, so imagine taking a backup and it streams all of the data and it gets up to sequence number 5,000. The next day when you reconnect, instead of saying, hey, I'm back again, give me everything, what you can do is say, I'm back again. Last time we spoke, you gave me up to sequence number 5,000. Can you just top me up from that point? And so it's a restartable service that allows us to do things like incremental backup. And in the event of failovers and things like that, when nodes fail, we can, instead of having to repopulate the entirety of a data set, we can just basically give the delta. And so this is used both internally within the cluster for replication, to send the updates to the indexer, to the FullText service, and it's also used externally. So external connectors such as Hadoop, it's used for cross-data center replication and backup, as I mentioned. So these three things, the multidimensional scalability, the automated sharding via vBuckets, and the transport protocol that we use, DCP, you're going to see these throughout the rest of the presentation where we talk a little bit more about the services. I want to very quickly flip to an actual cluster and show you how some of these are manifested. So let me see. OK, so here I have a cluster, a demo cluster I've set up. And I've actually set it up with exactly the same topology that I had in the slide. So I've got 6 nodes. You'll see in the middle here, 3 of which are running the data service, 2 of which are running the index service, and 1 at the bottom that's running both full text and query. So this is how these nodes appear in your cluster when they're running these different services. If we choose to add a server, you'll see at the bottom, you get to select, you get a very simple tick box of which services do you want, this node that you're about to add, which services do you want to run on that node? And that's how easy it is to administer a cluster using this multidimensional scalability. So, OK, let me just exclusively add some query capacity or exclusively add the data service or mix and match to whatever your particular requirement is. And then if we look in the buckets themselves, just to give you, again, a bit of a flavor for what's going on. So I've got a simple cluster here. It's not currently doing any operations, but you'll see in the UI we expose things like the vBuckets. So you can see we've got 1,024 active vBuckets, and they're evenly distributed, sort of 340 each across the 3 data service nodes. And also, the other thing to point out here is you can monitor the DCP queues, the replication traffic. So these mutations that are being streamed to each of the other services, you can see these in the UI, you can monitor them and see how they're performing. So even though these are kind of a little bit behind the scenes sort of architectural concepts, we do expose some of them so you can help monitor and understand exactly how the cluster is performing. OK. So with that context, I'll now turn it to my colleague, Dave Rigby, again, the technical architect of the data service, to start walking you through some of the services and how they operate behind the scenes. Dave.
Great. Thank you. Hi, guys. So thanks, David, for going through that. I want to dig a bit deeper into some of the main services that we expose. The cluster manager, the data service, the index service, the query service, and FullText Search. So the first of these is the cluster manager. As the name would suggest, this is responsible for managing the cluster. There's an instance of this running on every single node in the cluster. And if you will, it's the control plane of the server. It has 2 main components. There's a component called the babysitter. It's a very simple but important job, which is to monitor all the different processes that make up a node, which may vary depending which services you selected, and to start them, restart them, and monitor what they're doing. The second larger and more complicated part of it, which is what I'll mostly talk about, is NS Server. NS Server is essentially the brains of the operation here. It's responsible for cluster membership, which nodes are currently in the cluster, nodes that want to join, trying to remove nodes, and the health of those nodes and the status of those nodes, and determining if action should be required if any of the particular health metrics exceed acceptable thresholds. It's also responsible for service layout. So we saw the diagram of our 6 nodes and the different services we've selected. So we have an NS service responsible for making sure that the services that are running in the right place, how those services talk to each other, how they're orchestrated together. Reading on from this is data placement. So we have to place the vBuckets on the appropriate nodes. An active node, a node that has a vBucket that's the active copy, obviously the replica copies have to be elsewhere, and you can have a various number of replica copies, and as topology changes, it has to orchestrate where these things live. When we perform a controlled change of topology, so we're adding a node or removing nodes or multiple nodes, when we perform a rebalance, NSO is responsible for coordinating and setting up the data streams to move data from A to B, changing the ownership, flipping a vBucket from being replica to becoming active. And in a failover situation, which is similar but has some slight differences. So we have a situation where a node's health status isn't correct anymore, or there's a hardware failure, there's a network problem. We need to remove a node forcefully, fail it over, and promote the data that exists on a replica copy to become active to maintain availability of the data. As it's the cluster manager, it kind of controls the root of the authentication. So it controls the admin authentication, and it also delegates authentication down to the different data services to access the data inside buckets. And as we just saw in the UI, it exposes the admin API. So it exposes the web UI, which you saw, and underneath that there's a REST API, which essentially gives you the equivalent functionality so you can drive this in a more programmatic way. NServer and Babysitter implemented in Erlang. For those that you might not be familiar with Erlang, it's a functional language. It was designed very much for concurrent distributed fault-tolerant systems, very much like what the cluster manager does. And so it's a good match for what we actually want to do with it here. So if we dive into a bit more detail of what's actually going on inside the cluster manager. So starting from the top, we've seen the admin console and the REST APIs. And we have the authentication. We went straight to logged in console, but there's also the admin there as well. And now there's various collections of services that perform the various tasks that we've kind of outlined and others as well. The first set is per bucket services. So if you have 1 bucket, 2 buckets, 5 buckets on a cluster, there's a set of services which is replicated for each bucket. These are responsible for things like DCP management, so coordinating the data that's moving for that given bucket. And for some of the tasks I spoke about before, rebalance, failover, setting up vBuckets. It's responsible for stats collection that we just saw, so the stats for a bucket over time. Those are recorded historically, both for kind of analysis after the fact and also kind of immediate health that may affect things like failover and the monitoring side of that. We have per node services. So again, we have an instance of this on a given node. We have a heartbeating mechanism. So we send messages periodically to all the nodes to ensure that those nodes know the health of myself and they know that I am still here. And so either that heartbeat contains information saying I'm bad, or the absence of that heartbeat receiving can be used as a trigger to potentially cause a failover, for example. Babysitter is part of the per node services. Now, I said that the cluster manager runs on every node, and it's basically the same software. And so all cluster managers are kind of equal. But some nodes are more equal than others. And so we actually have this idea of an orchestrator which is elected to run on a particular node. So there's a single instance, a singleton in the cluster. And this is responsible for things which are cluster-wide. So things like the data placement. We have to have a single view of where the data lives. We don't want to have conflicting views of where data happens to reside. Rebalance and also failover are also handled by the master services. And on top of this, we have some stuff that kind of is a building blocks of these things. So we have generic distributed services, services which understand and are distributed aware, they're aware of the fact that there's a cluster. So things like the configuration, again, we need to have a global configuration or node C. This is replicated using gossip replication. And we have to be able to distributively discover new nodes. You can essentially add one node from any other node in the cluster. So when you actually log on to the admin UI, we happen to pick a node, and we can use any node because they essentially all forward information to each other. And there's also some local facilities that are used to build these things up. So the configuration stored locally, logging services, vector clock and UUID services to maintain consistency between these various services, and general kind of low-level primitives, work queues, other miscellaneous functions that are used as building blocks. So that was the cluster manager, a component that's responsible for the brains of the operation. So now we'll talk about the data service. As I say, if the cluster manager is a control plane of the system, the data service is essentially your data plane. It's the low-level data plane of the server. It consists of 2 main components, key value access, or KV engine, which I'll talk about in a moment. And there's an asterisk here. We also have map-reduced views. They are part of the data service because essentially that's how the system evolved. And they're more of an indexing component, so I'll talk about those in the indexing section shortly. So KV Engine, this is the evolution of the Memcached application, the Memcached protocol. And it's something that we've evolved over quite a long time now, adding various features to support the Couchbase server you see today. So we've added persistence, we've added this replication, we have this concept of vbuckets, the idea that you can have clones of data. And we've enhanced the APIs that Memcached exposes for some richer access. So for example, we can expose access to sub-parts of a document. We can modify and access particular pieces of a document, particular paths, things like counter support. So one of the things we've inherited from Memcached is this sort of asynchronous networking I/O. So we have a set of worker pools, worker threads that can asynchronously manage tens of thousands of client connections concurrently. And we have a memory-centric architecture. What that means is that when we accept mutations, we initially put them into in-memory structures, and asynchronously in the background, we arrange that they are persisted to disk, replicated out of the network to other nodes. And again, the data that is currently hot, that is most recently used, is kept in cache, is kept in memory in a managed cache. And so we can make most efficient use of the memory that's available to the system. And then if we have to, we can go down to disk and pull those things from disk as necessary. So again, we'll dive into this a bit. I'm going to skip through this quite quick, because I've probably got something which is maybe, I think is more interesting, which is kind of showing what actually goes on for real. So at the top, we have like a dispatcher. This is a component which probably most resembles the Memcached evolution. So it's responsible for handling all the network traffic. So it's dealing with request response, give me this document, change this field in this document, delete this document. It's also responsible for DCP streaming protocol. So streaming out those mutations, concurrently in a stream to any interested parties. And it deals with data authentication. So when you connect, is this user authenticated to this bucket? Can they access the data that resides within this bucket? For each bucket that we have on a node, there'll be an instance of KV Engine. The kind of a front part of this is a managed cache. So this is a set of hash tables which are partitioned per vbucket, both active and replica, depending on your topology. So the data will be written from there, the data will be accessed immediately from there. Associated with that is a checkpoint manager. This is part of the DCP infrastructure to allow us to have an ordered sequence of mutations. We know where we're up to in a sequence. People can resume from a certain point. And it's also responsible for arranging the data to be batched and written to disk. Each bucket has a set of tasks running. I've only shown 4 here. There's many more, but I'll talk about some of the more interesting ones. So we have an item pager and an expiry pager. These are both responsible for moving things out of memory as necessary on a document basis. So item page is responsible for moving things out of memory when they become less recently used, when we have memory pressure. We want to pull in other documents that are more recently used. Expiry page is similar, except it's responsible for removing things which have been expired. We have this concept in Couchbase of setting a TTL, a time to live on a document, so you can set an auto-delete in the future. And that's the task that's responsible for doing that periodically. On the disk I/O side of things, we have a fusher task, responsible for fushing batches of changes to disk, and a batch reader which does the inverse. It pulls things into the cache as necessary. All this runs on a set of shared threads. So we actually have 4 thread pools in the back end. We have a reader and writer thread pool, and a non-I/O and an auxiliary I/O thread pool. The readers and writers, so they're independent thread pools, so they don't affect each other. We can do concurrent accesses, reading and writing, without affecting the other. So I want to try and dive in and give you an idea of, we see lots of these rectangles and what do they really mean. I want to show you the journey of like a single operation through the system. So what I'm going to show you is kind of a very simple kind of setup, a very simple topology. I have 2 nodes that are only running the data service. I just have a single replica, Couchbase Server 0 and 1. And they have DCP replication running between them. And I have probably the world's simplest SDK application. It connects and it inserts one field into one document. That's all it does. It's going to insert the value connect 2016 into the hashtags field of tweets d Haikney. And what I'm going to try and do, and I apologize in advance if this kind of I lose anyone, but I thought this is kind of an interesting way of showing what goes under the hood. I'm going to show you the execution of this with a tracing library that we've implemented called Phosphor. That allows us to show what is actually going on under the hood and show the various flow of tasks over time inside the server. So let me just flip to what have we got here? I can just about see my windows. So I have the world's simplest demo application. So as I just said, so yeah, like we're going to connect and we're going to change a document. It's very, very simple. So let me run that. So I've got a script that basically is going to turn on tracing, run that demo, extract the trace into a HTML format, and OK, we're done. So let me flip over to this. So oh, this is how we see how big it will go. So hopefully you can kind of see this. OK, maybe this will work. So what I have here is I have the two nodes. There's two processes here, so I'll just collapse them a second. So I have trace node 0 and trace node 1. So these are the traces from each node. And you can see that the whole thing basically took, I don't know, 0.8 milliseconds. And each of these, this is a kind of a Gantt chart. So we're seeing time on the x-axis. We're going to have various different concurrent things on the y-axis. At the moment, we can just see the two processes, so the two nodes, essentially. So if I expand the first of these, we can see a number of threads. So we have worker 1 and worker 3. And we have a writer thread at the bottom. We have two non-IO threads up here. And I'll kind of dive into this and hopefully show you what's going on. So the first thing we're going to see is we can see the execution. We have a subdeck executor phase, which is performed with three main steps. We have a fetch of the existing document. We update it. We manipulate the JSON and make the changes appropriate. And then we update that to the various, we store that result. In the fetch case, we end up calling down into, let me just pull this up, a hash table read function, which seems to have taken, what's that, well, 1 microsecond approximately to actually grab the data from memory. It happens to be in memory. It's in the hash table of this particular vBucket. I believe it's, we should have it here, vBucket 1, for chances. OK. So then operate on it. We add that new field, and then we do an update. OK, so, and the update, you'll kind of see this is kind of taking a bit longer. But the first thing it does is queue the mutation. So we're going to enqueue this into the set of things that need to be persisted, that need to be sent around the system. And then we're going to do a notify. We're going to tell people who care that there's a new sequence number. There's a new sequence number available, and various actors in the system might want to do something about this. So the first thing that we'll look at, and I have to zoom out again here, is we have quite a long task here called Fusher step. So this is the Fusher task that I showed just before. And you can see this kind of kicks off pretty much just after the notifies happened on the writer thread. So a different thread of execution here. And it's going to perform a set. So it's going to call Couchbase Server set to actually set this new element. And then it's going to do a commit. Now, in most kind of real systems, you're going to have a batch of updates. And so you're kind of, this is a commit is basically rebuilding the B tree, inserting this new document, going down to disk, doing a data sync to disk. So this is actually, this is very much dominating the work here, which is to be expected when we're only changing one document. So it's taking, what's it taking? About 400 milliseconds, 0.4 a second in this case. Now, what we'll see actually is concurrently, if we kind of bounce back up again up here to this non-IO thread near the top, you'll see that this is another event which has basically been triggered by the notify sequence number available. The non-IO thread has kind of been woken up and said, oh, there's DCP connections that need to be notified. And this does some work. It finds out who needs to be notified of this particular sequence number. We may have many replicas, we may have many consumers, or we may just have one. And so as a consequence of that, that's going to basically tell the front end of the system, oh, the front end threads are doing the DCP streaming. And they're being told, oh, there's some new work, there's some new data to send out. And if I dive right in here, very much in, this is the DCP step function. So this has been told to step the DCP task forward, to step this queue forward. And it's generated a DCP message mutation. I'm just showing the vBucket here. It happens to be the same vBucket. Again, this is quite fast. This is all in memory stuff. This is kind of us pushing something to, we're going to do a write to the kernel, and the kernel's going to handle a network sending. And at this stage, this node is kind of done. He's done all his work. Just to kind of show, this sort of happened sort of in a kind of an instant, so to speak, compared to what was going on at disk. So if I just kind of collapse this down, just to kind of make some space on this screen. So this was what was going on the first node. If we kind of pan over to the second node, we'll see that we have something going on here on the worker thread. So the only thing we've got here is a worker and a writer. In the worker, if we dive in, we can see we've got a process request. So we're processing some request that's come in, which is a DCP mutation request. You can see at the bottom here. And that's being handed over to a DCP consumer. This is an entity that's consuming DCP as opposed to one that's producing DCP. And it's going to make a couple of calls. It's going to do a set with meta. This is a special kind of set. We already know what the metadata is here. We know all the additional metadata that's been carried by DCP. It's kind of a clone of the original set. And so there's kind of two main things happening here. We're going to actually update the hash table writes, again, very, very fast. And then we're going to queue it. So this is kind of the same thing we saw in the master. We're performing a... Ooh. Not quite sure what happened there. We're going to enqueue this to put down to disk. And again, we're going to see a very similar thing as we saw on the master. So if I zoom back out again, very much out. Fusher, again, we're seeing a commit. And this is probably going to be a similar duration to the first one. Maybe it's slightly different. But essentially, it's doing the same thing. It's now persisting the replica copy to the second disk. So we actually now have, depending on how you want to look at it, 2 or 3 copies. Well, we have at least the data that's in memory on the active nodes. We have the data that's in memory on the replica. And we have data now on disk on both of them. So we have a number of places where this data exists. Final thing I'll say is that one of the things all these different threads give us is that if we go back up to the top here and look at this guy here, he finished doing his operation and handed it off at this point in time. We could have then gone and handled an extra request for the next person or a second request from the same connection while all the other stuff is going on to sort out the persistence in the background. OK. Very good. Back to slides. So that was the data service, the low-level data plane of the system. And I'm going to talk about the indexing service. So strictly speaking, we have 3 indexing services. We have our incremental MapReduce views. These have been in Couchbase since Couchbase 2.0. They kind of were an evolution of the CouchDB MapReduce views. And these allow you to do efficient kind of aggregation and kind of complex map function application on data. You get a JavaScript map function, and if you can write in a JavaScript function, you can apply to a mutation. And these also support geospatial views, geospatial queries, so you could actually have some data where you want to draw a bounding box and say, of this data, what falls within this geographical region. And these are co-located with data service. The second, well, I'll go to the third. The third kind of indexes are FullText Search, which David will talk about shortly. These have their own indexes, but they're quite differently structured because of the way that they have to deal with the sort of free-form, full text aspect. So the indexing service that I'm kind of referring to here, sort of, as the main title, is our global secondary indexes, or GSI. So these are intended to be efficient indexes for secondary lookup, so looking up by something other than the key of a document. So I had a tweets example here. I had a user that was a primary key. Maybe I want to look up by a region or an email address or a handle or something such as that. And so GSI gives us that secondary lookup, which we can then use for ad hoc query processing using our NoSQL query language. So again, I'll dive into the architecture of this. The first place we're going to start is actually on the data service, because the first part of the indexing service is co-located in the data service nodes. So we have a data service. We have 2 buckets in this example, and I have a DCP stream, which is streaming the changes to this bucket to the indexing service. And so the first component is a projector and a router, or router, if you will, which is, as I say, co-located on the data service. And the role of the projector and the router is to try and answer the question, is this mutation relevant to the indexes that exist? And that's actually kind of a subtle question, because we have a document that may have, it's essentially free form. A particular update may have certain fields, it may not. And a certain index definition may or may not care about that particular field. And so the projector and the router are essentially index aware. They know about the definition of the indexes that exist. And they can basically compare that definition with this one particular mutation at a time and say, OK, well, you've got an index in this field, but this document doesn't contain this field, so I don't need to bother about it. Or, OK, there's an index on this field, but of this large document, the index is actually concerned with 3 of the fields. So it will do an extraction process and send the data that's relevant to the indexing service, which may be on the same node, or it may be on a different node, as we talked about for multidimensional scaling. So the projector and a router, if they've determined that this data is relevant, they'll send it on to the supervisor on the index service. So again, the index service, we may have one or more indexing nodes. Each one is responsible for a number of indexes, and there'll be a single supervisor on each indexing node, which is essentially responsible for maintaining that node. So main two things it's responsible for is index maintenance. So that's creation of indexes and removal of indexes, bringing in new mutations that are sent to it from the projector, and applying those in a consistent fashion so we can view the indexes in particular positions in time. And then it's also responsible for the other side of the coin, which is, okay, what do we do with these indexes? There's no point in having them if we can't actually make use of them. So the supervisor is also responsible for coordinating requests that are coming in from the query service for requests. And the query service basically is requesting index scans. It's saying, please give me an index for this field, maybe based on a certain range, maybe constrained by certain factors. Underneath the indexing service is essentially two choices of how that data is persisted. We have our standard indexes, which were added when we first introduced indexing service in 4.0. These support arbitrarily large indexes which may or may not fit in memory. So they can become data greater than memory, and they can be, we basically will spill to and from memory into disk as necessary. What we recently added in Couchbase 4.5 are memory optimized indexes. And so this gives you another choice. If you have an index which is is sufficiently sized that you can fit it entirely in RAM, then you can choose that one, and you can actually get a higher mutation rate. You can actually sustain a higher mutation rate from the data service. So next call out, memory optimized indexes. I've only very briefly touched. We have a talk this afternoon in this room here, Grace America 2, from Sarath, talking about memory optimized indexes. I really can't say that. How they work. So again, if you're interested in the architecture side of things, that's a really interesting thing. So I'll hand back to David, who's going to take you through the query service and FullText Search.
Thanks, Dave. Just to let you know where we're on this journey, we've got 2 services to go. So hang in there. We've got a few more rectangles to see yet, and we'll get to the end. So you've put your data into Couchbase. You've indexed the data. Now you want to query it. So I'll talk you through how that works in a moment. But first, I thought it'd be interesting to show you a few queries. So let's flip back to our cluster. And again, because it's election day, we thought I've downloaded all of the recent tweets from the 2 candidates, some from Donald and some from and stuck them in a bucket. So I've got, I think, about 3,000 of each. The last 10 minutes. And so what I've got here is a query, and I'm going to choose the favorite top 5 hashtags of each candidate, just so we can sort of see what they're tweeting about. So you'll see the query here. Selecting from my Connect 2016 bucket where the screen name we'll go with Hillary first. And I'm pulling out all of the hashtags and the text field within the hashtag. So these tweet structures are reasonably complicated JSON documents. They've got kind of nested entities. And one of the really powerful, interesting things about Nickel is its ability to interrogate even these hierarchical structures. We've got these nest and non-nest terms that allow you to dig deep into the JSON documents and run queries on those. So we're going to pull out all the hashtags, group them together, count them, and return the top 5. So let's see what Hillary's been tweeting. Here we go. So here's the results of this query down here. Top query, 54 hashtags. Hashtag debate night. Dems in Philly. Hashtag VP debate. Hashtag debate. Clearly Hillary's up for a debate. And let's see how about Mr. Trump. So we change the screen name. I think he's real Donald Trump, something like that. And off we go. There's a prize if you guess what the top one is. Okay. Mr. Trump, 268, so clearly he likes a hashtag slightly more than Hillary does. Mr. Trump, Trump 2016 hashtag. Hashtag Make America Great Again. Hashtag MAGA, if that's how you say it. And this particular, when I was running through this example, this one chuckled me. Because imagine being British and having no context whatsoever what the hell this means. Hashtag Drain the Swamp. Go on. Well done, Donald. It was a mystery to me. So either you've got, on the one side, you've got debate or Make America Great Again. Maybe if you're on the fence, maybe make America debate again. That's the common middle ground. Okay, so that's a query. Let's look at how that works. So client, as you just saw, the UI in this case makes those query requests. And the first thing that the query engine does, the query service, it parses it. It checks for syntactic correctness. It understands what it is that you're trying to query. It will then construct a plan. It will then say, OK, for all of the indexes I have available, which of the indexes are able to satisfy this query? Which of these indexes satisfy the query most efficiently? So based on the query that you input, it'll come up with a plan of how it's going to fulfill that. And there's an optimization we've recently introduced. So if you're running the similar queries frequently, you can actually cache the version of that plan in the application. So you can send back the plan. And so the next time you make that query, you say, here's the query again. And you can skip the plan step because I've already got a plan for you. It'll then go and scan that index, as Dave described, and pull out all of the relevant documents. And then maybe the query needs some other field. So we were scanning for documents where the screen name was one of the candidates. And then we were going and fetching those documents from the data service and pulling out the hashtag field. Oh, dear. I think that's a sign I've spoken too much about the election. And so this is then there's a pipelined process where all of the rest of that stuff you saw of pulling out the fields, of joining them together, of doing any joins, doing the aggregation, doing the sorting, and then ultimately pushing the results back. Again, this follows on from our theme of multidimensional scalability. So all of these operations are operating on multiple documents in parallel, and the query service is going to take advantage of as many CPU resources as the node has. And again, if you find out you're starting to do more queries, or your queries aren't coming back as fast as you like, you can add more query service independently of the rest of them. Couple of fantastic talks at Connect. So Keshav, who's floating around somewhere, he's at the back of the room, I can see him. That's actually following on from here, I think in this very room, of how to understand and use the query optimizer. So it's easy enough to write a nickel query. Even I was capable of doing it. It's quite a skill sometimes to write the most efficient nickel query. So Keshav's your man for pointing the way at how to do that. And then what if you want to do something more interesting than Donald Trump's top 5 hashtags? So a talk coming up tomorrow morning in Great America K about how to do more creative, more interesting things using nickel. Final service to dip into is FullText Search. So you can think of this one as kind of Googling or grepping your JSON documents. So this is in the business of taking your JSON documents, and it's going to receive a feed of mutations, again via DCP, this replication protocol that we've spoken about quite a bit. It's going to index those, so it's going to rip out all of the real text words, and it's going to store them away in an index. And the way it does this, the user will, I'll show you a demo quick in a second, but you create the index using the REST interface, perhaps the UI on Couchbase Server. That index definition, maybe you want to index the entirety of the document. Maybe you just want certain fields from within it. So you create an index definition that's stored by the manager. I'm feeling there's like some sort of bad voodoo going on with all these lights flashing. The manager stores that in the configuration. The index that's. And then a planner says, OK, right, I'm going to split this index into a number of partitions. Again, it's going to shard it in exactly the same way we do with the data service and the vBuckets. So splitting that one index down in a bunch of partitions here that they're described as p-indexes. And if I've got multiple full-text nodes, I can spread those around the cluster. And again, I can keep a replica copy of the indexes, so I can have the availability. I can dynamically move those indexes around for the scalability when I rebalance, etc. And some of the magic here is performed by Blevy. So this is a standalone Go component written by a chap called Marty here at Couchbase, used by products other than Couchbase as well, but we use it. It's a full text parsing engine written for Go, and that's where we do all of the lexical analysis, the word stemming, etc. So let's take a very quick look. Let's go back to our cluster and see how we both create an index and then query one. So I've gone to the Indexes tab. I'm selecting full text. Again, I'll create a new index. I'm going to choose my bucket of tweets. And I don't want to do the entirety of the document because there's all sorts of metadata in there. So I just want the text field, and I'll call that something like tweet content. So this is me creating that index definition. So describe it, hit create index, and then hopefully, oh, I need to give it a name. So tweets, I'll do. OK, create the index. And off it pops. So it's only a small data set. It's only about 6,000. We can see it's chugging its way through. And then when that index is built, we'll be able to query it. So I hardly dare ask, but does anyone have any suggestions of what we'd like to, give me a word that we can search for in these tweets? In the absence of any suggestions, let's go with swamp again, because I enjoyed swamp. OK. So here we go. So I've selected the index I just created. I whack swamp in, hit search, and there we go. A bunch of tweets talking about the swamp. So that's how easy it is to create a full text index. And so again, this is just a very quick flavor for the real meat on full text, how it works and what you can do with it. We've got Steve Yen, the co-founder of Couchbase, along with Marty, who was chiefly responsible for that Blevy component, are going to give a fascinating talk tomorrow at 1 p.m. And then very finally, just before we wrap up, not going to dive into this, but really exciting news that in addition to full text, we're introducing an analytics service into Couchbase. So you're going to hear a bit more about this at the keynote. It's hugely exciting development, and we're going to look to introduce that as a developer preview and make it generally available soon. So you're going to find out more about another service. So next year, there might be more rectangles for you to sit through and enjoy. And so there's as well as the keynote, Till Westman's going to be giving a talk on this tomorrow at 2 p.m. So you can see how we're going to incorporate the analytics service into Couchbase. OK, and we're done. We're at the end of the rectangles, the end of the services. So hopefully that's given you a flavor for some of the Couchbase fundamentals, how we achieve the performance, the scalability, et cetera, and how each of the services are constructed. Many thanks, and enjoy the rest of Connect. Thanks.